Hi, everyone. We're going to look today at a type of differential equation called separable. So we have a couple of examples of separable differential equations that we're going to do here. Now, a differential equation is any equation in which we have a derivative as an unknown. We're going to stick to first-order differential equations. In other words, differential equations in which we only have first derivatives. But you can have second order, third order. You can have things that are a combination of those. We're going to start with a pretty straightforward one. So we are going to solve dy dx equals y squared. And we're specifically going to solve it for values where y does not equal 0, because if y does equal 0, then we just have dy dx equals 0. So just if y does equal 0, then we have dy dx equals 0, which means we just have y equals some constant. This is considered a degenerate case. It's not that it doesn't exist or isn't relevant, it's not really the point of the equation we are trying to solve. So we are going to solve for the case where y doesn't equal 0. Now, the reason that this is separable is because essentially I can separate the dy and the dx. These are called the differentials. So I can have dy, for example, equals y squared dx. That's not how I want it. I actually want each differential with its variable, but this is separable because I can do that, because I can separate everything that has a y from everything that has an x. In other words, I can write this as 1 over y squared dy equals dx. If I can do that, if I can separate it, and we'll look at equations where I can't separate it, but if I can separate it, then it's pretty straightforward because I can actually just then take the integral of both sides. And I now have an integral that I can evaluate on each side of this equation. I have 1 over y squared dy, which I can evaluate. That's just a power rule, y to the negative 2. So I can increase it, y to the negative 1 divided by negative 1. So I end up with negative 1 over y plus some constant. I'm going to give it a subscript here. You'll notice that that's a trend in my early steps of these differential equations. Anytime I put a constant down, I'm going to give it a subscript because my final constant isn't necessarily going to be the same as my initial constant, and I want to be able to reserve just c for that final constant. On the other side, I have the integral of just dx, so in other words, 1 dx, which is x plus some other constant. Now, you'll notice right off the bat, those two constants, I could actually just put a constant on one side of the equation. That is actually what we're going to do. So I'm going to write this as negative 1 over y equals x plus some third constant. And as a matter of practice, as I move along, when I've separated out my differential equation into the y's on one side of it and the x's on the other side, I'm not usually going to bother putting a constant on the y side. I'm just going to put a constant on the x side with the understanding that that constant includes both constants. Now, if I want to isolate here, I've got y then equal to negative 1 over x plus c3. This is my final step. So at this stage, I can drop that subscript. So my conclusion is going to be that y is equal to negative 1 over x plus some constant. You'll notice that when we've had more complicated differential equations now, the constant doesn't just always show up as a plus c at the end. So in Math 31, you can get a little bit, lazy and just always be adding c onto the end of whatever you get. Here we have to be really careful that we're adding the c in the right place because our end result, the c isn't just a constant being added on. In other words, the relationships between the different solutions to this particular differential equation are not just separated from each other by vertical translation. That was the case when we were doing really simple antiderivatives, that it creates a family of functions that are all just vertical translations apart from each other. And that's typically when we have a derivative that is defined solely in terms of x. But as soon as we start defining it in terms of y or as some combination of x and y, then it's not as straightforward. In fact, so this is just the general solution. I don't have a point on that, so I can't come up with something more specific. If I look at the slope field for this function, for this derivative, So this is the slope field of dy dx equals y squared. I can see that, there's some relationships between, so I can kind of see general, like if I put one solution on there, maybe another solution up here, the relationships between these things are not just straightforward vertical translations. There's something a little more complex going on. So that would be the first one. Going on now to the second example, where it gets a little more complicated, just in terms of the integration as well as the separation. So let's say we have dy dx, and that is being multiplied by x squared minus 1 plus 2y, and we know that this equals 0. It's fairly common in differential equations to have your derivative being multiplied by some expression or some variable or combination of the things. So in order to separate this, I'm first going to actually isolate the dy dx. That often helps me sort of see how the separation happens. It's definitely not a thing you have to do. It's just a way that I sort of visualize it. So if I've subtracted the 2y on the both sides of the equation, and then I divide by the x squared minus 1, here is what I get. Now I can tell that it is separable because y exists on one side of the fraction and x exists on the other side of the fraction. So if I think of this now, I'm going to have 1 over, and I'm just going to do 1 over y. I'm not going to do the minus 2y. I'll leave the minus 2. Basically, I'm just dividing both sides of the equation by y. So I'll have 1 over y dy equaling to negative 2 over x squared minus 1 dx. This is now fully separated, so now I can integrate both sides of this equation. When I do that, I have the antiderivative of 1 over y. Well, this is going to be the natural log of the absolute value of y. I'm not going to add the constant on this side because I'll just add a constant on the other side. To integrate this expression over here, negative 2 over x squared minus 1, I'm going to need partial fractions. So I'm going to say that negative 2 over x squared minus 1 is equal to something over x plus 1 plus something else over x minus 1. So that means that ax minus a plus bx plus b is equal to negative 2. In other words, a plus b equals 0, and negative a plus b equals negative 2. Just some linear system solving. So if I add those two equations together, I get 2b equals negative 2, which means b equals negative 1. And since a plus b has to equal 0, that means a has to equal 1. So now what I'm integrating is 1 over x plus 1 minus 1 over x minus 1 dx. These are now just logarithms as well. So the natural log of the absolute value of x plus 1 minus the natural log of the absolute value of x minus 1. Here is where I'm going to add a constant. I am calling that C1 because I'm not at the end. I have some isolating and so on to do. I am on the right-hand side of this equation going to use a log law to combine these things. So I'm going to actually express this constant as the natural log of some other constant so that I have all logarithms and I can combine. It's just a different constant, but the point is it is still a constant. So I now have the natural log of the absolute value of y equals the natural log of, I'm just going to do this as all, it's a little bit of a cheat. So actually I've got C2 times x plus 1 divided by x minus 1, which means that, and here's where I'm going to be definitely smoothing some edges here, some nuance that we are losing a little bit of. So I've got y equal to C2, whatever constant that is, times x plus 1 divided by x minus 1. Or just more generically, now I don't need the subscript, y equals some constant times x plus 1 over x minus 1. Now, I've ignored a lot here. Specifically, I've ignored a lot with regards to those absolute values and potential domain and range issues. The reason I'm ignoring them right now is because they're not really the nuance we're going for. They definitely matter when this is defined, when the function is defined versus when its slope is defined. The slope was only undefined for x equal to positive and negative 1. You'll notice that this original function is not defined for x equal to 1, so that at least is consistent. But through the middle here, I've got some work where it's sort of iffy whether x can be positive, y can be positive, negative, not relevant for what we're doing here right now. So that is definitely something that you'll explore later on in other courses. So right now, we're just worrying about the mechanics of separating the differential equation and getting your results. The other sort of way to think about this is taking the natural logarithms and dealing with those things where we have these restricted domains. Those are intermediate steps. They're useful tools that we're kind of leaning on in the middle of our work. Ultimately, what would matter is matching up, for whatever application I'm dealing with, matching up the relationship between this function now, y equals some constant times x plus 1 over x minus 1, and the slope function. So the dy dx equals negative 2y over x squared minus 1, and making sure that those are lining up. Now, if I were going in the other direction, so if I'm looking at this and saying, okay, what if I started with the function y equals c times some constant, let's call it 7, times x plus 1 over x minus 1, I can derive that very simply using quotient rule and never have to use natural logarithms. And so it's a little more straightforward in that instance what our permissible and non-permissible values are. So we don't worry too much about that as we're solving the differential equation. Just in case you were curious, let's look at what the slope field of this differential equation looks like. A little bit like this, where we can see we do have some elements of the curves of, well, that one's a little bit weird, but we do have some elements of rational functions going on in here. I don't think this plotter does a really great job with asymptotes, but here we have it. Yeah, it definitely isn't doing a great job with asymptotes. The nicest one is this one, but you can see it's drawing a vertical line on there for asymptotes, which is somewhat problematic. That's a limitation of this grapher. All right, and then the last equation that we're going to look at in this lesson, we are going to actually have an initial condition. So for this one, we'll be able to figure out what that constant is. So we are going to solve the differential equation dy dx equals x squared y with the point, with the knowledge that y at 2 equals 1. So that's going to help us figure out the constant value, but we basically start the exact same way as if we didn't have that initial condition. This one is separable. I've got 1 over y dy equals x squared dx. So a little bit nicer in terms of the integration we're going to have to do here. We're not going to have to do any partial fractions. It's just going to be straightforward. On the left-hand side, I've got the natural log of the absolute value of y. Again, I'm not going to be too picky if you don't write that absolute value of y. It's just a decent habit to have. But because in the end, we're going to kind of ignore it anyway, it doesn't really matter. And then on the right-hand side of my equation, I've got x cubed over 3 plus some constant. Now at this stage, I'm not using a subscript because I'm actually going to pop over to the side here and figure out what that constant would be. So I've got the ln of 1 equals 2 cubed over 3 plus some constant. The natural log of 1 is just 0. So 0 equals 8/3 plus that constant. So that constant is negative 8/3. So I'm going to substitute it in at this stage. So now I've got the natural log of the absolute value of y equals x cubed over 3 minus 8/3. So actually, I'm just going to write that as x cubed minus 8 all over 3. And here I'm going to get a little bit sloppy and drop the absolute value. And I get that this is therefore e to the power of x cubed minus 8 over 3. So that is the specific function that we're dealing with in this case.